I should start with just a word of background, which will help to set the proper intellectual tone for this discussion. I'm a university professor, and what is a university professor? It's, a university professor is whatever it is, but it's an honorary title, and when I got this, I said, this sounds terrific. What good does it do me? I mean, do I get more salary? No. Do I get more space? No. Do I get more support? No. Then what's the point? And what they said was, what it enables you to do is to teach a course in Harvard University on any subject, regardless of whether you know anything about it or not, to students regardless of whether they're interested or not. And in that spirit, I'm going to tell you about commercialization, because what business does a chemist have in talking about commercialization? And the answer is, I'm talking about it. So unless you'd like to make a point of it, you're going to have to listen for a while. Well, let's see. Okay. So I want to start with a deep philosophical question. And you say, why would I ask this question? Why is it not disgusting to think about commercialization? And the answer is that if you're in a science department, and probably many of you are engineers, the general notion is that if you're thinking about commercialization, I can't describe just how bad this is, how deep the moral decay is to think about this, because we're supposed to think about fundamental research. Now, what's fundamental research? And at that point, people go get another drink and go on and think about other things. But so the basic idea that thinking about commercialization, making things real, is but in science departments, definitely. So I want to give you just a couple of reasons. There's an ethical reason, which is that unless your science becomes real, it never benefits anybody. I mean, we do a lot of work in technology for the developing world, and the amount that your typical, Ugandan, and I say Uganda because we've done a bunch of field trials there, cares about papers in Nature and Science is actually pretty limited. They care about diagnostics. A second is obligation, because I remind you that somebody's paying for your research. I'm going to come back to this. And so it's not that you are entitled to research, it's that you earn research somehow. A third is support for society, because if people don't understand what you're doing, and they don't understand condensed matter physics, you say you're talking about condensed matter physics, and I'm paying for it? I mean, give me my money back. And that's not because they're not happy with it, it's just they have no clue of what it is. And unless you can explain it best by showing how it's real, people are not interested. Creativity, one of the strongest arguments is that if you work on problems, and problems both in terms of subject, but also problems in terms of the style in which you work, you tend to get locked into an eddy. And the nice thing about commercialization is that it brings you into contact with a whole series of ideas having to do with finance and this and that, which you just never come into contact with if you're living entirely in an academic department. Training, I assume that some of you would like to have jobs when you're finished. And jobs come from being able to do something that somebody wants to have done. And if what you're doing is not something that somebody wants to have done, you can argue you should get your money back because you haven't been trained to do anything. And then finally, there are a series of things that I won't go into, which are very important, which are based on the interface between national security and technology, which require conversion to reality. So there are a whole bunch of reasons for wanting to do stuff that's real. It's not just making money. I couldn't care less about making money. And I would say for those of you who are interested in commercialization, the first thing to think about is that if you want to make money, go to work for an insurance company, invest your salary wisely in a high yield, low load mutual fund, and forget about it, because you'll actually do better that way. It may not be as much fun. Okay. So let me just give you a couple of examples of problems. This is one we were talking about at lunch. And that is, if you're thinking about a problem in medicine, we have two models in, let's see if I can go backwards. Can one go backwards? No, one can't go backwards. Anyway, remember the picture. This is called the second law of thermodynamics. You can't go backwards. Time reversal is poor. The point is that we have a model for healthcare which relies, and you need to think about it. Conflict. The issue with conflict is that we have gone from something which is high technology, that is force on force in the folded gap, to things in which there's conflict in Afghanistan, basically small groups of people. Relatively low cost, and to an area of conflict which is actually extremely interesting, which is called commercialization. Because what countries fundamentally compete for now is jobs, and compete for schools can benefit from them. And I just point out in passing that another very interesting part of conflict is down here. And I was at a war game a couple of years ago in which I was playing the side of a group of things in which the major competitors were governments combined with very large corporations and advocacy groups against other corporations and non-state entities. The whole world is shifting out from under, and the business of commercialization and money has become a critical part of understanding what national security means. All of you are dressed well. Some of you are a little plump from eating too much. And this is good, but it comes with a wealthy society, and a wealthy society requires new ideas. And don't think that you're going to be alone in this in the future. This, very big deal. I don't want to spend time in studying these things, but there's just a point to make. And that is, these are charts that you're perfectly familiar with, which are, this is men in dark, women as a function of age in a society, the percentage of these. And the thing to understand is, with Japan, there are very few young people. Unless Japan solves this problem, they will go out of business. The United States is relatively balanced, but only because of immigration. And this is, I can't even read it from where I'm sitting, but somewhere in the Middle East, it's all young. And young males who are unemployed are guaranteed trouble. And this is part of what's going on. There are no jobs in the Middle East. And so this is another part of this whole subject. These issues are familiar to everybody, but I point out that nobody cares where the water comes from when they turn on the tap or when they plug in the electrical cord. They don't care whether it's clean electrons or dirty electrons. All they care about is affordable electrons. And these problems are very well posed. But to come up with a new idea is really, really hard, and a new idea makes no difference unless it's pumping electrons into the line. So that's commercialization. And then we have begun to invent some astonishing structures. And one of the ones that interests me most is megacities. And I don't know, I think this is a composite shot of megacities. But think of Mumbai or Beijing. These are cities now with more than 50 million people. 50 million people. The world has never seen this kind of structure. I think you can make some very interesting claims from them. But the technologies to manage these, suppose you were driving a bus called Mumbai. What would you do? And we have no idea how to do it because the technology for doing it doesn't exist. These are big, interesting problems. So, there's no question about problems, and I can list any number of others. How about obligation? This is something which I think all of you should think about, and that is, how does stuff, if you're a taxpayer, how do you get to the point where you understand that what's going on down here is of any use to anybody? And the way it works is the following. Taxpayers, which may be corporations, give money to government. They do so because if they don't give money to government, they go to jail. But also because there is an implicit belief in a stable society that something good comes of that. The government gives an insignificant fraction of that to universities, which are supposed to produce you plus good ideas. But since the university generates no products, there's an interplay between universities and corporations which generate what are called products, and the products are seen as benefit. But you can learn a lot if you follow the money. It's not a bad thing to do, even in the wonderful halls of universities. Now, This is a very interesting chart that's the basis for much of the debate about public policy in the United States. How many of you have seen this chart before? Not so many. Okay. So it's worth the effort going through. This is called Pasteur quadrant, and it was originally developed, I guess it's not on this slide, by a guy named Don Stokes at Princeton. It's a very interesting point of view. And the argument goes as following. We have said for years that we're going to divide the world up in terms of basically curiosity-driven fundamental understanding, low interest in this or high interest in some subject, or consideration of use, low interest or high interest. And why is it a 2x2 chart? And the answer is this comes out of the world of Bain and Co. or McKinsey, in which 2x2 is as far as you can go as an analyst. 3x3 is impossible. So we have 2x2. And so the argument is that you have, to personalize this, you have things divided. So pure basic research is named by Bohr, who quite correctly was not interested in commercialization. You have Mr. Edison in high implied research, and Mr. Edison truly believed that if you wanted to make a better filament, you got bamboo and ox hooves and all, he had this giant warehouse full of stuff that he used for all kinds of things. And he actually violently opposed science. He thought it was a waste of time. So here is what we argue in universities, tend to argue, is that what we should do is be spotlessly clean and do this. And then this is the job of industry, and that's what they do. There's a third point of view, which is the Pasteur point of view. And I should review what Mr. Pasteur did, because it's relevant to the discussion. Pasteur, you think of in terms of pasteurization, which sounds pretty uninteresting. But at the time, it was revolutionary in two senses. What Pasteur did was to note that food and milk spoiled rapidly in France. And he then, by empirical experimentation, figured out that if you heated the milk briefly, it didn't spoil. And moreover, he noted that when it spoiled, there were little things swimming around in it, little animals. And after you heated it, they weren't. So he solved the problem of spoilage to an extent. But more importantly, he invented the area of applied microbiology. And he's often given credit for that. He's also often given credit for being one of the first to use vaccinations. And I forget what he vaccinated for. I think he was the first to do rabies, but I could be wrong. And so he's often given credit for being the father of applied immunology. What he was doing has a structural characteristic that I think is worthwhile paying attention to. What he was doing was taking a problem that's a really important problem, spoilage, disease, for which there was no scientific solution, and then inventing the science that made it possible to solve the problem. And this is what I argue for all of you to think about. There's nothing wrong with solving a problem and using a problem to stimulate your creativity and to think of new ideas, but you haven't really solved it unless it becomes real for the society that pays for it, and that's commercialization. So that's the argument, and I make no bones about the fact that I believe in this use-inspired basic research. This area down here, which has low fundamental interest and low applied interest, is often called, forgive me, the university quadrant. And that's not where you want to be. Now, if you want to invent quantum mechanics, I promise you to write a check myself. And if you'd like to invent light bulbs or the transistor, I'll write a check for that. But this is not good. Okay. So the argument is what we just went through here. And the red, I think, is a bad idea. So pay attention to that. Now, I want to give you, I'm not generally in the business of shilling for books. But here are two books that are worthwhile reading. How many of you as students have read these two books? A couple of students. Are you a student? Yeah. These are two books that are very, very worthwhile reading. I won't go through the details, but let me just give you a sketch to whet your interest. This by Kuhn. What am I doing here? Here we are. This by Kuhn, over here, is called The Structure of Scientific Revolutions, and it has to do with the best that comes out of curiosity-driven research. And what he argues briefly is that 99% of the work done by scientists is making sausage. It's just turning a crank and out comes stuff. And it's not creative at all. I mean, he actually has some good things to say about it, but it's fundamentally imitative. And he said that, what these problems, he calls them, nomenclature is not great, he calls them puzzles. And what they are problems in which you know what the answer is before you start. You basically know how to get there. You know you can get there. Nobody cares whether you get there. And you do it just because you like the technical problem. The other 1 or 0.1 or 0.01% is what he calls a problem. And by that he means something in which you don't know that there's an answer. You don't know how to get to the answer. You basically launch on this as something which is a great experiment, and people really care about the answer. And his illustrations were a cure for cancer and the quest for world peace, and fill in your own illustrations. But the point is that most of what's called curiosity-driven research is actually bad engineering. And his argument is that this is fine because you don't know whether current theory fits current practice unless there's some current practice. But it's a pretty expensive way of doing it. Okay, that's point A. Point B is this wonderful book, which is a book which describes the history of Bell Labs. And I have devoutly resisted reading these kinds of things because so many of them have the basic style of Bell Labs created the universe by brilliant physicists striding forward unfettered by financial or economic constraints and following their imagination, and it was just wonderful. It turns out that there's no question that Schrieffer and Bardeen and Shannon and the rest of these guys were brilliant physicists. That wasn't the issue. They were making a more profitable telephone system. There were people in New York who wanted to pick up the telephone and call someone in San Francisco and order cows or whatever. And they couldn't do it because the switches didn't work. They couldn't get the signal across the country. So all these guys worked on that problem. But it was absolutely driven by utility. So any idea that the way to do it is just to look in the mirror and find that you yourself are the most stimulating thing that you can find, there are better things to paste on your mirror than that. All right. I'll mention one other bit of background which is relevant, and that is most of our scientific system right now is based on a document by Vannevar Bush, who was the science advisor to the president in World War II, who wrote something called The Endless Frontier. And without going into details, he justified the existence of the modern research university, ours and yours, based on 3 ideas. That is, the country needs this federal level investment to deal with the creation of jobs, development of systems of public health, and national security. Punkt. Very applied. So the idea has been corrupted into the idea that there's an entitlement to science to develop whatever it wants based on whatever creativity it can come up with. Nobody ever imagined that being the outcome. So I just remind you of these, and now we're going to go on. And my argument is that in a research university, you don't commercialize something, you don't have anything that people can see. And the question now is, the rest of the talk, how do you get there? Well, a couple of more things to pay attention to. It's always good to examine habit. And there are 2 habits which are pernicious. One of them is the academic habit, which thinks of the world we live in as, I write papers in order to satisfy the peer review system, to give me money, to do research, to write papers, to satisfy the academic, this is not a way that anyone but a white mouse should spend any time. So that's not a good thing to do. The second is the corporate point of view, and the corporate point of view, I'm sorry, I'm not very bright, the corporate point of view says that the purpose of a corporation is only and exclusively to make money which it returns to stockholders. and that in fact there is a fiduciary responsibility of the board of directors to maximize the return to stockholders. That is factually incorrect. I mean, the point of view, the purpose of the board of directors is to maximize the health of the corporation considered as an individual. And that can be long-term, short-term, embedded in a society, doing who knows what. But it's not just to make money. It's something more complicated. So in this area of innovation and developing new stuff, which is what we're in the business of doing, there's endless, really entertaining reading. My colleague and friend, Clay Christensen, invented something called the innovator's dilemma. And what Clay says is that corporations rise and fall based on disruptive innovation, meaning you used to have adding machines and you come up with computers, or you have rotary dial phones and you come up with G7s that burst into flame spontaneously, whatever it might be. And so he's sold 1 million copies of this, and his, at least for a while, his lecture fees were substantially higher than what I'm getting, if anything, here. So I bring this up just for management to consider. I mean, this is a small thing. Then my also much admired colleague, Jill Lepore, who, as people have said, writes faster than anyone can read. Jill is full of really great ideas, and what she says is that absolutely everything that he says is wrong. And that the way good ideas come is that big corporations innovate. You know, they add a mile per gallon to fuel, they change the front bumpers a little bit to make it safer, they do this tinkering. And I think Jill is right. But there are occasions in which big corporations are displaced by new technologies, but the big corporations never invented the new technologies. It almost always came from little corporations. So, innovation. Now, if you go to the center of the book, there is a very, very important lesson from Bill Baker, who was running things at the time. I think it's Bill who said this. I have to look it up. And that is, he was asked about which we do, and it's coming up with new ideas, whatever that might be. And that's pretty easy. And then there's a phase which he called invention, and that means prototyping an application for something. And of course, in universities, we consider ourselves as pretty daring when we think about prototyping something, you know, as opposed to just writing a paper saying that somebody else could prototype something. Then there's development, which is a long, hard process in which you take a prototype idea and you actually make it work. You do the engineering work to make it work. You think about quality control. You think about manufacturing processes and regulatory clearance and all the rest of it. And then that leads to a product. And typically we say, we're there, we've got product. And his point is that you do these things and you have nothing. That none of this makes any difference. The only thing that makes a difference is market. And what is a market? A market is an aggregate of people who pay you for your product enough that it's worth your effort to develop that product. And that's very different from a product. And as I'll show you as we go along. But so the development of a market is everything. And it's something which small companies do badly, big companies do badly, universities do badly. And if I had one thing to argue, I would say what we can do is to think about identifying, thinking about how to build markets in a way that made it possible for very good university systems and very well-run corporations to do something new together. All right. How does this translate? We've been through this. In the academic world, people will talk endlessly about science. They'll talk endlessly about innovation. They may talk about product, and that's it. And there is an issue here that's important, and which justifies some of that. And this is a remark. But the people who invented the transistor never imagined a billion trips with 10 nanometer design rules in a circuit that you sold for $7.21. It just never occurred to them that this would happen. And an interesting number to put in the back of your mind is that a friend of mine who does this for a living, I asked him how much money has gone into the development of current, sub 20 nanometer design rule electronics. He said about $1.3 trillion. That's a good number to put in the back of the mind, as I say. Then the commercial point of view about this is you say, what's the chain of events? And the answer will be pretty clear. Market, I've said that. After market comes capital. After capital comes more market. After that comes more capital. And then maybe you have to worry about product at some point, but that's sort of assumed. So the 2 points of view are so different. This is where the real valley of death is. It's not making a product out of science. It's at this issue where you understand that it's market and capital that makes commercialization, not just a good idea and a product prototype. Very different points of view. Capitalism in the market. And this is, again, something you'll get. I'm on a number of boards of directors, and my colleagues are mostly good, hard Republicans and capitalists, and I'm a good, hard Democrat and a capitalist, so it's okay. But they really believe that the objective of a company is to provide a return to its investors, and the United States a little bit to distribute ownership, and it makes and generates and provides products and sells them to customers, and that's it. So you don't do anything else. I mean, that's okay, but that's only a part of the issue. So when you're thinking about commercialization, you've got to think about these different points of view. Now let me just give you one or two other things to think about. One of them is that if you think about this process very crudely, science, invention, engineering, product, and ask how the costs of these scale, it's in the order of 1 to 10 to 100 to 1,000. Maybe not quite, but it depends on the circumstance. The reason why that's important is that all the money goes into the downstream stuff. So all the resistance to spending the money is on the downstream stuff. What you have to do is to convince people that it's worth their effort to put in the very large amounts of money that are necessary to create a market, which involves, for example, hiring salesmen. One of the companies I'm working with right now is selling a new product in the biomedical area. We're spending $50 million a year just on sales development. That's a lot, it turns out. So the second is, and I think this is another good thing to keep in mind, that every new technology, you can argue about these things, costs greater than $100 million. It can be between 100 and 500 million, and takes in the order of 15 years, maybe 20, maybe more. So these numbers are right almost across fields, with the possible exception of apps and software, where the development costs are small and commercialization is small. And here's the second thing, and this is something which is an estimate that comes from some work we're doing on diagnostics. And it basically asks the question is, what does something cost? And the answer here is that if we make 100 tests, it's going to cost so much that it's astronomical. 1,000 tests cost $10 a test, 1 million is one, and 100 million, so on. In order to get down to the target that we have, you have to get in the order of 100 million tests. And you say that's megalomania. But it's only 5% of the population of India and Africa. And what that means is to actually have something that is produced at scale, so that the price becomes low enough that it can be used for everything, you have to make a gazillion of them. And if you look at the number of chips, number of transistors made per second now, the number made per second is some billions of transistors per second worldwide right now. It's just unbelievable. You ask where it's going, and I assume the world has the smartest toaster ovens you can imagine. Okay, and then it's the curve of time and risk discounted cash flow. And since in order to make something real, you have to get money, and since the government will only pay for a small part of it, the rest of it has to come from somewhere else. And where does the somewhere else come from? And let's say it's investors. And what they want to know is only, I can give you money, I can put it in savings bonds, or I can put it in Bahamas real estate, or I can put it in immunogenomics, or whatever it wants to be. How do I do that calculation? And the way I do the calculation is the following. I say that what I'm interested in is the total amount of money that I spend. Here it is. And so I spend some money on research, but by the way, I have to borrow that money, and I'm paying interest in that. So if I look at that integrated amount of money that I've borrowed, and the interest I pay on it, there's a curve that would go to minus infinity here. But somewhere in here, I start getting a product, and the product begins to bring in revenue. And so in a successful program, what happens is that the amount of money coming in here integrated pays off this, and eventually you get to the point where you're actually making money, cash flow becomes positive. What's important about this is that it says that the less you spend on research, the better. And the shorter the time between here and the crossover point, the better. So time is bad and risk is bad. And what that means is that you want to do things fast and for sure. And that doesn't mean you start on a basic science program and just, dawdle along. And understanding that makes it much easier to understand why, when you go to big corporations and say, I have a good piece of science, why don't we make some product out of it? They say, oh, we love your idea, we'll call you next week. And they will not call next week. Okay. Then there's sort of a final issue metaphor to put in mind, which is a common one in Cambridge, the Cambridge venture world, and it's what's called the Anna Karenina phenomenon. And what is that? If you're starting a company, you have to have good science, you have to have good management, you have to have good people, you have to have facilities, you have to have investment bankers who understand what you're doing, you have to have a CEO, you have to have access to a market, you have to have, there's this list of things. If you get any one of them wrong, all 50 of them, you fail. What's common about successful companies, they've gotten all 50 of them right. So there are 50 combinatorial ways of failing and one way of getting it right. So this is not trivial to do, and you want to think carefully, and the way you think carefully is to reduce risk and time and cost. Here's just a list of some of these things. Now, against that background, I'm going to say something which I think is worthwhile paying attention to here, because this has to do with the US, which I know better than Canada. But it also, those of you who know Canada will find that there's some differences between the US and Canada, and these need to be thought of carefully. We probably both have technical workforces that are creative, skilled, and mobile is a more complicated issue. Canadians don't like moving as much as Americans do. And creative in different ways, I think. We both have good research universities, but they're different in their scope and what they're intended to do. The isolated local ecosystems are very different. One reason the US works is that we have Silicon Valley, we have Seattle, we have Boston, where there are whole industries that are based on supporting this. And in Silicon Valley, if your little company goes out of business, no one cares, because the technicians just go to the next little company. There's no job insecurity there. It's all upside. We have a culture in the US that's very different from much of Europe, and I think different to some extent from Canada, that we value wealth. We think it's good that people make a lot of money. We applaud entrepreneurs, and we applaud hard work. Particularly in France and Asia and some other countries, you'll find that even though everybody says they agree with all these things, they don't actually agree with them at all, not at all. Societal system that's comfortable with elitism. We like the fact that Mr. Gates has made a lot more money than anyone else has. And then a series of incentives that are actually pretty important. For example, capital gains taxes are a really important component of our system of innovation, because it makes it worth the effort for people to take risks, because they pay less in taxes when they succeed. There are a bunch of these which are technical and I think a little bit off track for this discussion, but it's good to at least know they exist. End of the first half. Second half. What I'm going to do is just give you some war stories. And these are just some of the companies I've been involved in. And there are a couple of points to make here. One of them, these are ones in red, are ones I'm going to talk about briefly. These are ones I'm not going to talk about for no particular reason other than they're mostly earlier stage. There's a point which is worthwhile looking at here, and that is if you add this up, it turns out that these things, which don't misunderstand, I don't take credit for this at all, but by the time we're done with all this, there'll probably be $40 or $50 billion in capital worth created. And that's enough that when you go and argue with your local administrators, you can make a case that this is not a trivial component of creating jobs. Take $20 billion or $40 billion or whatever it is and divide it by a couple of $100,000 per person per year, and you get an idea of how many jobs that you're creating, and money comes back, and it's all important and interesting. So let me just go through some of these relatively rapidly. Geltex, one of the first ones we did. Its product was a non-adsorbed organic polymer to adsorb ions and molecules from the gut. And the original idea in this was, I'll go through this in a little detail for those of you who are young. A guy who's become a good friend and a venture capitalist, who was giving a talk at MIT on something. At the end of it, came up and he said, "Hello, my name is Jim Tannenbaum." He was your name, your age. He said, "Let's start a company." And I said, "Okay, why not?" I had no idea who he was. And I checked on the telephone. He turned out to be a smart guy, so why not? And I said, "By the way, do you have an idea?" And he said, "Well, yeah." I said, "I've licensed some technology." And so I looked at the technology, and it was clearly wrong. But it took me a little while to figure that out. And having done that, the technology was around gels. I said, gels are interesting, so why don't we think about it? And so we thought about it. And eventually I came up with, I thought, a really good idea, which was to make a gel which would absorb sodium ion from diet, because this was in a period where we thought sodium was important. And we actually put the company together and started to make this stuff. And then I did the calculation of how much of it would you need. And to deal with the sodium in one big McDonald's milkshake would have required 2 kilograms of gel. This seemed like not a good idea. So sort of in desperation, we said, is there anything you could do? We couldn't think of anything. But it still seemed like not a bad idea. So we hired a consulting company, and they went off and they thought about it expensively. And they came back and said, this is really a stupid idea. And the only thing you could possibly do would be to take out phosphate. But phosphate is only a $40 million a year market, and so you get half of it, and you'll never pay for the effort of getting through. So we started out on phosphate. And the end result was that it turns out there were 3 products already in the marketplace. One was some ion exchange resin, one was Tums, and one was calcium acetate. Turns out that most people who are on this are elderly, and eating ion exchange resin is like eating sand, and it degrades your colon and your anus. And so, this was not considered good for patient compliance. It turns out that if you eat enough Tums, you will get an aluminum-induced Alzheimer's, and they killed a number of people with Tums. And the third is calcium carbonate, which for reasons I still don't fully understand, if you eat enough calcium carbonate, you disturb the parathyroid hormone balance, and you start mobilizing calcium, and you develop osteoporosis. So all the competition failed. And it turned out that dialysis is expensive. So the last time I looked, this stuff was selling something north of $1 billion a year of this. So which is a little bit bigger than 20 million. Now, I would like to take credit for all of that, but I had nothing to do with anything except setting this group of smart people off on a really bad track. And they made something of it anyway. Here we go. And so the second, actually there may be a slide that gives you timeline for that that'll come up. It's probably out of place right now. The second is a company called Advanced Magnetics, which had the idea of doing ferrofluids, and it's another classic example of the Anna Karenina effect. Here we are, yeah. And what it did was this. And it made, All right, that's in the right place. What it did was to make a magnetic colloid, and you can see 20 nanometers. For those of you who are in nanotechnology, this is about 1970 or something like that. And we thought these would be interesting. And you inject them into the brain, and because they're super paramagnetic, what they do is to magnetize and change the relaxation rates of water in the blood, and allows you to visualize, here's the cerebrovascular circulation, and here's a tumor in a breast. And you would think that if you were a surgeon, the patient came in with this amount of information, that you would be very happy. The answer is that it was never approved in the United States for the reason that the company could never demonstrate that that level of information actually provided value. Was the patient better off? And it was really impossible to predict, because those sorts of clinical trials are very expensive. They last for a very long time. And so this is something you have to pay attention to and think about. But anyway, the company started in whenever it started, and did an IPO here, and galloped along with this MRI imaging agent, doing almost nothing. And at this point, totally by accident, it found that if you gave this to patients, this stuff to patients who had undergone chemotherapy and had damaged their hematopoietic system, it rapidly helped to reconstitute the iron part of that, which is erythrocytes, and that has become about an $800 million company now. And so, did I say totally by accident? I think I did, but yes, you get the idea. Here's the third, and this is actually very interesting in dealing with this issue of market. We spent a lot of time on this, and what our interest was using our skill in chemical analysis to deal with the problem of how you provide low-cost diagnostics in the developing world. This was driven by ethics. I didn't plan ever to make money on it, and I promise you I have not. But the basic idea was to set this up in such a fashion that we would do invention, and then, since we are not engineers and we don't do engineering, we put together a separate corporation, a 501c3, to do the engineering development. We realized that would work. It was explicitly not for profit. The objective was to make the lowest cost technology, and there's a lot of commercial interest, and it's failed. Not irreversibly, but why has it failed? And the answer is that if you look at, well, let me come to that as we go along. How does it work? Here is the starting point. It's just a coffee stain on your expensive linen napkin. And if you look at this, what you find is there's a splatter here and wicking. So the idea is that we would use the ability of an aqueous solution to wick into paper to drive it in such a fashion that you didn't need pumps and electricity to do that. That was the underlying idea. And that has worked out just fine. So the time to go from here to a prototype, and this is printed in paper to provide a hydrophobic barrier. You put a drop of urine in here, it wicks its way up. Brown indicates glucose in the urine, and blue indicates protein in the urine. And nothing is required other than just that and some stuff I'll show you in a moment. From here to here was just a couple of years. And that's very rapid for a diagnostic. And this basic idea works just fine. And so how do you do the patterning? You basically take an inkjet printer, you use something called solid wax, which is designed to go on the surface of paper, but you melt it slightly, it permeates the paper, and it makes hydrophilic paper hydrophobic. So that you can go from a basic idea to a product prototype in a morning. I mean, it's really straightforward to do. And here's the basic design of the system: a piece of paper with a hole in the center, it's hydrophilic, a little disc to filter out erythrocytes, put a drop of blood here, erythrocytes filtered out, goes onto another pattern thing which has colorimetric reagents, and you're basically there. And the test was designed to do this: drop of blood, which is about all you can get practically. You can't do blood draws, and there are many parts of the country in which you're actually very constrained. Muslim countries, you're very constrained in even how close you can get to the patient. And so this is a serious issue, women patients. And so you get a drop of blood, you apply it to this, you wait for 20 minutes, erythrocytes filtered out, and you read the color. That's as simple as we could make it. You couldn't do anything more than that. And the same technology, if you extend it, makes what I still think is probably the best, for example, RNA handheld system. This is really a very good system, which was designed originally for pediatric AIDS, redesigned for Ebola, and is now being worked on for different things. Now, what is the point here? How could this not succeed? The answer is to take the liver function test, which has been through large field trials in Vietnam, works fine, to take it to CE mark clearance. Just to do the lawyer work is $2 million, and people will not give you $2 million just to do it. To develop this thing into a commercial product would take about $10 million, and people will not give you $10 million. Well, you say, but look, this can do handheld DNA analysis. Their view is, fine, we're very interested. We will take it once it's cleared, but we're not going to take it on spec. So that's part of the market. I mean, until you have it through regulatory clearance, you don't have anything that looks at all like a product. And even after, you don't have a market. And that's the part where you need to be very careful in your thinking. Now, actually, I think something's again out of whack. Let's see, yeah, here. What we did was also to look at electrochemistry. And you say, electrochemistry, why would anyone do electrochemistry? And the answer is that if you look at blood glucose analysis for diabetes, the number of tests done electrochemically for blood glucose monitoring for diabetes is larger than the total of all tests done by other technologies in clinical medicine. So electrochemistry can work. So we put together this very nice system, which you see here, which interfaces with a crappy old Nokia G2 phone. Why that? Because it's the only thing that's going to be available for probably 20 or 30 years in Africa. And this thing is probably about $5, I don't know, lower than that in bulk. And this is what it replaces, and that's probably about 20 to 30,000. And for those of you who are electrochemists, I'll put in just a smidge of data. And because it's run on either a Raspberry Pi or an Arduino, you can simply put any program that you want into it, so you can do very sophisticated electrochemical experiments this way. And you want to change the experiment, you just download it. It's terrific, really works very well. Having said all that, it leads to another set of interesting issues. If you go to some developing world place very often and you say, wouldn't you do a better job if you had better equipment? And they say, well, let me show you something. And they go to the closet and they open the closet and it's stacked with beautiful equipment. And you say, well, what's wrong? And they say, 3 times a day we get 1,000-volt surges going through our power lines when breakers don't break. And our motherboards last for about 2 days. And at the end of that time, we have a beautiful piece of equipment, but we can't fix it ourselves, and we can't get anyone to come and fix it, so it's useless. So if somebody wants to invent something, find one of those intermediate step-down transformers that will somehow even this stuff out so it's not that much of a problem. I don't fully understand the problem myself. But why did this fail in the first issue? It's a successful technology. It's basically set up the right way. This liver function test is a good test, and it is basically okay as a class 1 device, but it will go on there. But there's this problem. You say, what's the problem? The problem is that in the United States, in Europe, nobody needs this kind of test for most purposes because you have Quest and Roche. You do a blood draw, it goes into a robot which does a really great job very economically. There are specific circumstances where this doesn't work, but there's no real market, and in any event, Roche and Quest will try to kill you if you try to introduce a competitive product. If you go to Africa, there is absolutely a need, or India, absolutely a need, but they don't have any money to pay for the development. They would probably pay for the product, but they won't pay for the development. So there's no market. That is to say, there isn't enough money in either place to justify the development. And that's what I mean by market. It basically has to do with the money that's available, not the technology, although obviously they interplay. So this is the timeline here, and I've sort of gone through this, and I should just say, lest you worry, that we've restarted with a new business model which has to do with a paired not-for-profit and for-profit enterprises. And one of the things to remember is that innovation comes in three flavors. There's technology, there's process, and business model. We've got the technology problem solved. This is basically either a process or a business model innovation, and I'll tell you in a while whether it works or not. Third company, or fourth or whatever it is, Theravance. The idea here is that the technical idea is that in looking at biological interactions, particularly, for example, viruses, they usually attach to a cell by not one receptor interacting with one ligand, but rather with a number of receptors interacting with a number of ligands weakly. And our idea, and very well demonstrated, is that if you use a polymer that has a number of ligands, you can compete with this interaction. So it's an idea that actually is a pretty sound idea. So what happened? We started it and pushed the wrong button. We started it, and it turned out that we decided after a while that this good idea of polyvalent polymers would never get through the FDA for the reason that they didn't know how to deal with a polymeric product. How do you specify purity and things like that? And there are one or two, but it's just excruciating to do it. So we switched to the idea of oligovalency, and this led to something which was a critical component, and the critical component had to do with a collaboration with GlaxoSmithKline to build what turned out to be the products beyond Advair, Rio, and Anoro, which are finally doing pretty well. This happened because one of the members of our board was Roy Vagelos, who had been the CEO of Merck. It wouldn't have happened otherwise. That's another issue that you have to think about. Who's going to help you in this kind of thing? And so this has gone on, and it's done fine at this point. It was a 96 start, and at this point it split at some point. Several other things happened, but the value of these companies and capitalization is $2-ish billion, something like that. So it's doing all right, but for reasons that have only vaguely to do with the starting point. And what I'm going to close with now, after those examples, to give you a notion of how polyvariant this is a bunch of little aphorisms. And I want you to think of me as being your uncle. And I'm trying to save you from embarrassment and financial ruin if you want to be an entrepreneur. And I'm going to tell you some things to think about it. So here they are. First is, there are sort of three ways of thinking about things. You can solve a problem, you can develop a technology, or you can improve or imitate something that exists. And I think all three of them can be made to work in different ways. But remember this, and this is important. There's a difference between people who want something and people who need something. So you may want a new car, but you can put it off. But if you've got cancer or Alzheimer's, you need it, and you will pay for it. And so that element of urgency comes from with having a new idea. That's an argument for having a new idea. Second is that radically new ideas are much, much harder to do than Me Too ideas. They may or may not be more profitable. Big companies make their way by doing a lot of Me Too stuff. In the pharmaceutical industry, we're always ecstatic when some company gets to market with a product ahead of us because they're out there spending money convincing the FDA that it works. And it's much easier to come in as second or third, much easier to be a fast follower. Third is, before you think about starting a company, finish the science. I mean, if it's still interesting science, it's not appropriate for a company. And it's useful to keep in mind because we tend to say, it's such interesting science, we're going to do the science and develop products, and this is all going to be terrific. It's not going to be terrific. It's just going to spend money. So get the science done before you start. Fourth, establish what you're trying to do. And this is actually a pretty complicated issue. It's okay to make money. I mean, that's a good capitalist objective. It's okay for your university technology transfer office to want to make money for the university. But that's not the same thing as creating jobs, goods, and services for society. So Harvard right now has a big endowment. We actually don't care they want to cover the cost of things, but it would be more to Harvard's advantage to have the reputation of strengthening the economy in eastern Massachusetts to make another $1 million here or there. So you need to get straight what you're doing here, because it sets a whole bunch of things having to do with licensing and patents and stuff like this. It's really important. And it's important that you know what you're doing before you get involved in that. And then sometimes we, as I, have involved myself in this problem of trying to deal with a problem in society that capitalism can't solve. And I'm not sure that's possible, to be honest. I mean, maybe with an app, but basically you need more money than you can generate in any simple way. Consider what these things are, and I've said this before, but a customer is somebody who will pay you something. Expression of interest, not interesting. Money, check in the bank. A product is what they'll pay you for, check in the bank. And a market is there have to be enough of them that it's worth the money that you'll have to put in to develop the product. And it's a pretty straightforward calculation. This is actually pretty interesting. I was giving a talk in the medical school to the incoming MD PhD class, a lot of whom think they want to be biomedical entrepreneurs. And I am at least distant member of the Boston biotech mafia, meaning a bunch of people who've started companies and have scars of various sorts to prove it. I was having dinner with a group of these people, and I said to them, what is the one lesson that you would say to young entrepreneurs? It was interesting that everybody at the table came up with the same one, which was this. That is, do not try to do it de novo on your own. Go and find a company, and if necessary for free, just follow the CEO around. See what he does, she does for a year or two. And Marin mentioned my son, George, who's ended up, I'm sorry, you mentioned my son who ended up as the CEO of Virgin Galactic. When he came back from some trip abroad, he said, Dad, will you see if you can help me get a job that was sorting Xeroxing or something like that. Instead, he got there and he had this little card that said, George T. Whitesides, executive intern. And what that meant is he went to every board meeting, he went with the executive team when they went off and did business deals, he did all sorts of things. His mouth was sealed, but he saw how this group of good businessmen were making decisions in the context of that industry for a whole bunch of time. And it was just unbelievably valuable. Then he went on from there, and he was he was involved in NASA for a while, and then he went off and did Virgin. But you need, 5 years or so of actual experience in the industry before you understand why people spend money and what they're spending it for and what the concerns are. You just can't do it de novo. Maybe a little thing that you do and you run it for a couple of years and you sell it for a couple of $1 million, but if you're doing something serious, you have to do something else. Use venture capital as little as possible. Remember, venture capitalists are there to make money, and they're good venture capitalists. I have good friends, but they're basically the great white sharks of the world. And so they're not your friends. There may be exceptions, but they're not your friends. Oh, and this is actually an important point. This is another one of those confusions. VCs overvalue capital. And what does that mean? And that means when a company is sold, there's a certain amount of money. And you could say, how do you divide it up between the people who had the idea, the people who did the work, the management team, and the people who put in the money? And the answer is essentially all goes to the people who put in the money. So one of the lessons is that if you're a scientist and you want to make money, do not do it by starting venture startups, because they just don't work very well, because other things happen. So don't do it for that reason. Universities tend to say, well, we've done this brilliant piece of science, and so it's worth a lot of money. It's not worth anything, basically, until it's converted into a product. And then universities don't know how to start companies, and if they don't know how to value the technology and they don't know how to start a company, what do you do? And you'll figure it out, right? Or maybe you've already figured it out. Make it as simple as possible, because every complexity comes back and bites you. Remember the 100 to 1,000 rule, and it'll help you to understand where your money will be spent. Remember that you can't do technical development unless you do market development. So technical development to make papers is useless. Technical development to make a market in a company is appropriate. Regulatory agencies, every product will have to go through a regulatory approval process. Expensive and difficult for the FDA, less complicated for other products, but there's always that. And no regulatory agency is motivated to do something risky. Their whole notion is not to do that. Time and risk, discounted cash flow is everything, and slow and uncertain are both bad. There is an advantage to small companies, which is they're creative, but they have a very high cost of capital. There is an advantage to big companies, which is they have a very low cost of capital, but they're very uncreative. And the ideal world will be one in which we learn how to mix things, and we don't really know how to do that yet. This is another important one for those of you who are thinking about it. Go get a book on elementary accounting and learn all the words. Because I don't know what your disciplines are, but when you go into the real world, what you talk about is EBIT, EBITDA, and RONA, and all the rest of this kind of stuff. They're all accounting terms. They're all very straightforward for scientists to learn. But you've got to know them as part of your vocabulary before you start, because the world of business works on finance. Now, one other sort of interesting point, just to give you an idea of an opportunity and also a risk. I'm a chemist, and we used to have a model that said in the university what we'll do is we'll make something and then we'll sell it to BASF, and BASF will make a lot of it. It turns out that BASF is irrelevant now. And what's happened is that the center of gravity has shifted entirely to the consumer end companies. So if the original idea was BASF will make it and sell it to Google, now Google says to BASF, go make it. So what you have to do is not convince BASF to make it, but to convince Google to buy it. And it's a totally different dynamic. So the suppliers have become captives to the consumers. And it's something which permeates the entire world of big companies. Now, it's one reason why none of them are making any business and making any money, because their finances are being controlled by their ultimate customers. And I think that's the end of it. So what you should come away from for this, what should you come away from? Aside from the fact that I can't work this as a university professor. What you should come away from is that there's this fascinating business of doing curiosity-driven science, but it's not curiosity-driven science unless it's fundamentally new. And unfortunately, I have to tell you that the peer review system doesn't favor fundamentally new stuff. And then there's the other end of it, which is how do you commercialize stuff, which is critically important. And ideally, you want to come in with a product which is new, but by the way, it's more expensive and more risky, and that's hard too. And so I've just said there are these two things. They're both hard problems, and they're not overlapping. And I think that if your children and your grandchildren are going to have secure, prosperous lives, we've got to figure out this problem of how to put these together. Otherwise, the available capital and the available money is going to be spread over the surface of the globe as a thin film. Because, you know, people are going to continue to spend stuff, but we're accustomed to getting most of it. And if you want to help us continue to get most of it, you've got to come up with new ideas and figure out how to solve the problem. So I can help you to think about the problem, but the solution to the problem is more difficult. Thank you very much.